All right, well, let's keep going. Programmer-defined functions. So, all of these functions that we've been looking at so far are predefined functions. Somebody else wrote them for us. But we can write our own and display 4.3 is an example of a function you could have written yourself for total cost. And we're going to be writing our functions in two parts. So there will be a part that goes at the top above the main part of our program, or the main function. Might as well call it a function. That's what it is. This is called the function declaration, sometimes known as the function prototype. And basically what it does is it gives us the type of data that's going to be returned, the name of the function, and the types of data that are expected in the argument list. These are the parameters, or also known as the formal parameters. In this example, they have called them number par and price par, just to indicate that they are parameters. The other part is the function definition, and that has this same first line, which is now called the header. And then it's followed by the body of the function. And we put that after the main function. The reason we do that is a function has to be declared or defined before we start using it. And what traditionally was done was all the functions would be defined at the beginning of the program, and you had to, any function that some other function was going to call, you had to define that function that was going to be called first before the function that called it. So somebody decided it would be simpler if we just declared all the functions first before the main function, and then it wouldn't matter what order we defined all the other functions because we've got them all declared and we're not going to be calling them. By the time we call them, the compiler will know exactly how to build the function call. A function has a return statement in it. That's where the value is going to come from. That is the type of value that we told it our function returns. And by default, our parameters use the call by value mechanism. So they are known as call by value parameters or formal parameters. And what happens is whatever arguments that function gets called with, those arguments values will be passed into the function. Basically, they'll be copied from this memory location in this function to a new memory location that we can refer to by this value. And that will be done in the order of the parameters. So the first argument will go into the first parameter, the second argument will go into, or the value in the second argument will go into the second parameter. So at the point we call that function, those values get copied, and we start executing this code. When the return is encountered, that value in the return gets calculated and passed back to the calling location. So it would then get assigned to that variable, and execution continues from that point. If your function returns a Boolean value, it can be used anywhere that we use any other Boolean value. So an if can be controlled by the value returned by a function, for example. You can also leave off the names of the formal parameters in the declaration, not in the definition, but in the declaration. So we could just declare it like this. Most people are going to declare it with the full names because that just makes it a little easier. You can just copy that line as your header and so forth. Because they're passed in the order that they're listed, you want to make sure that your arguments are listed in the right order, same order as the parameter list. So they have an example of being passed in the wrong order and the code failing. And they talk about the rules on page 202 and 203. Spacing and line breaks are just like we've been doing so far. And they talk about how you can use function calls as parts of other statements to simplify them, kind of like I simplified my code for the blackjack game by using function calls. Some more self-test exercises on page 203. What is the output of this code that has the mystery function in it? Mr. Brantley.
Sure. My guess would be W.
All right. Well, let's take a closer look at it. So we're going to output right here, the results from mystery with the arguments 10 and 9, followed by OW. So the first parameter was 10, the second parameter was 9. So if 10 is greater than or equal to 9, that's true, right? So we're going to return the W. So the output is going to be WOW. Okay? That makes sense, everybody? The W comes from the function call, and then the OW was part of the line. Let's go on with more about functions and how they work. Procedural abstraction. Procedural abstractions means we can have code that we don't know the details of, and we can use it without knowing the details of it. We say that it functions like a black box, and that we use information hiding. And because we use information hiding, we call that procedural abstraction because that procedure, we know in abstract what it does, and as long as it works properly, we don't care what the actual code that's running inside it does. So on page 206, you've got display 4.7. Here are two functions that are black box equivalent, meaning they produce the same results. They look the same from an external point of view. The first one calculates an interest amount and then adds it to the original balance as part of the return statement. The second one takes the balance and multiplies it by the fraction of interest plus 1 and returns that thing that it calculated. It's calculated slightly differently, but it's functionally equivalent. And you need to choose your formal parameter names the way you choose any other identifier names. Something that makes sense. That's not going to confuse the next programmer that comes along. So if you're calculating a total cost from a number and a price, it makes sense to call your arguments or your parameters number and price. They also have a nicely nested loops example that goes back to our vulture egg counting program that we saw back in chapter 3. but instead of nesting a second loop inside our first loop, they call the getOneTotal function. And the getOneTotal has a loop, which is broken. I wonder who their proofreader is sometimes. All right, then they have a buying pizza case study. I'm not going to go through this line by line because I'm going to spend a little time on the homework instead. But it's an example of solving a problem starting with the problem definition. Then they give you the input and the output. They analyze it, break it down into subtasks. They implement some of those subtasks as functions. And then they code each of those functions. And then they have a sample buying pizza program that have those functions coded in it. And they talk about testing your program. And you'll notice that they chose an integer for the diameter and the price. No, diameter, just diameter, sorry. So your pizza is an even number of inches. But if you are not careful when you're calculating the area of your pizza based on that, you could end up with a problem. That's an integer, and you're dividing by 2 to get the radius. Also an integer. You need to do a static cast in order to get a real number in case your diameter is not even. So a 14-inch pizza would work, 12-inch pizza would work, but a 9-inch pizza would produce the wrong results. And they're reminding you of pseudocode. So when you're writing your program, you can write pseudocode. That can be particularly useful when you're coming up with your list of subtasks that you have to do in order to solve the problem. Also, you're going to need to start putting comments on all of your function declarations that tell you what value is going to be returned by that function and what arguments it's expecting you to give it. Yes?
The variables you call whenever you're calling the function, are
Yes.
they local for that function? Like they won't be recognized anywhere else besides there?
Do you mean you're talking about the arguments that you call it with here? No, those are not local here. Those have to be defined in this function in order for you to be able to call them. Now, they are local to this function, meaning
there's a diameter and price of the ones I'm talking about.
diameter and price here.
No,
This diameter price. Yeah. Those are only defined in the unit price function. So the arguments, the parameters for a function are local to that function, just like any variable you defined inside that function would be. That answer your question?
Mm-hmm.
Okay. So you could have 15 different functions that had parameters that had the same names if you decided to do that, and the compiler would not get confused because each of those would go with its own function. Speaking of local variables and the scope of those, the next section talks about local variables. And you'll notice in display 4.11, we have average P declared inside the main function. We also have an average P declared inside the stotal function. Those are two different variables, and they're completely independent of each other. This average P only occurs inside the stotal, and this average P only occurs inside of main. And you'll notice that the IDE keeps them separate for us. When we highlight the one here, it does not highlight the ones in the other function. That's because the scope of this variable is this function, and the scope of this variable is this other function. They're local. There is such a thing as a global variable, which the book encourages you, and I also encourage you not to use. Global variables can cause problems because you never know when somebody in some function might decide to change your global variable, and it can make it very difficult to track down. Global constants, on the other hand, since they are constant and cannot be changed, make sense, and you're encouraged to use global constants for any values that you would otherwise code inside your program or a particular function in your program. So this is a global name constant, and from now on, if you have a constant value that you're going to declare in your program, it's going to make sense to make it a global declared constant most of the time. We talked about this just a minute ago. Call by value formal parameters are local variables. Just like the variables that we declare inside the code are local to that function, the parameters themselves are also local. and they work in some ways just exactly like variables that we declare inside the body of the function. They're obviously different because a value gets put into them when they're called, when that function is called by the arguments. So the value of the argument is copied into the parameter so that we actually can use that value. And indeed, any code block, anytime we have those curly braces, we're creating a block of code that has its own scope. So if you look at display 4.14 on page 227, our for loop is a block of code that has local variables. This I is a local variable in the for loop. The body of a function has its own local scope. And in fact, we can put a block of code anywhere. It doesn't have to be part of a loop or anything else. And the stuff that we do inside that, if we declare new variables, that new variable is only going to be defined inside that block of code. Not defined outside. Next section is about namespaces. When we say using namespace std, we're saying we want to be able to refer to identifiers that are declared in the std namespace. That's the one that's used by a lot of libraries, including IOStream. And they're going to want you now to only use the namespace that you need when you need it. So in display 4.15, they want you to put the using namespace std inside the function that it's actually needed for. So in the case of 4.15, it's actually needed in main because we're using cin and cout, and in area because we're using pi that's in the math. No, not because we're using pi, because we're using pal that's in the math library, and also volume is using pal. But if we weren't using pal or cin or cout in our function, we wouldn't need the using namespace std. Display 4.16 is showing the fact that a parameter is a local variable and how you can use that to your advantage. We can call this factorial function with a value, and we can actually alter that value while we're inside the function. The argument that we call it with is not going to be affected because it's a call by value argument. So it allows us to use it kind of for double duty. We retrieve the original value and then we can alter it as part of our function, and it saves us from having to declare another variable and initialize it to that value. Another thing we can do when we're writing our own functions is overload function names. Overloading means that we call a function by the same name, but it does something different. And the thing that it does different is based on what's called its signature. Signature is the number and type of the arguments or parameters that it uses. So this is a really simplistic example that they use here, but they have an average function that averages two prices on page 232. And then they have another average function that averages three prices, or three numbers together. So the first one has two arguments. It's called AVE. The second one has three arguments, or three parameters. It's called AVE3. And obviously, we know we have to use the AVE3 one to average three numbers if that really made sense to do that. But by overloading, we can call them both AVE, and the compiler will know which one to call based on the number and type of the arguments we give it. So if we call AVE in display 4.17 with three values, we are actually calling the function that takes three, or that has three parameters. And if we call it with two values, two arguments, we're calling the function that has two parameters. So they go back to the pizza pricing program, and what they're going to do is, in addition to, well, instead of comparing two round pizzas, they want to be able to compare a round pizza and a rectangular pizza. So they now have two unit price functions instead of just one. The one unit price function that we had before took the diameter and the price to find the unit price. The new function takes the length and the width and the price. So compiler won't get confused because we have these different number of arguments that we get called with, and we can compare the unit price of a round pizza to the unit price of a rectangular pizza. It makes sense because the unit price name refers to what it does, and they both are basically doing the same thing, just with different dimensions. But you can tell that if they're being treated differently because of the different number of arguments. There is some automatic type conversion that takes place without you having to explicitly do it. And that's when where the program is expecting a double or floating point number and we supply an integer. Because we can do that without losing anything. So we can do that when we're initializing, or if we're passing it as an argument. It's going to automatically convert an integer into a floating point number for us if the variable or the parameter is expecting a floating point number. All right, a few more self-test exercises and then we can talk about the homework. Ms. Hernandez, number 24 on page 239, has two function definitions, and they want to know which one would be used in that function call. Sorry? Okay. Well, how is the compiler going to decide? Do you remember? Number and type of arguments. So this call has one argument of type double. So what function definition does that match? It's going to match the second one here. Because the second one is expecting one argument. It has one parameter, it expects one argument. Okay. Mr. Rahim, how about number 25? Now we have two functions. One has two doubles and one has a double and an int as its parameters. X and Y are both double. Which function is it going to call when we call it with Y and 6.0?
The first function.
It's going to be the first one. It's got two doubles The first one is looking for two doubles. All right? Mr. Gear, a little bit harder. How about number 26? We call it with 5 and 6. Which one is it going to call?
You use either one, couldn't it? Because it can convert it to double. I mean, they're both integers.
Yeah, it could convert it to double. But what the compiler is going to do is going to find the best match.
So the second one.
So it's going to use the second one because
Double and the one.
it's going to convert the first one to a double. The second one is an integer, so it's going to say, well, that matches this signature better.
Why?
Why?
Yeah.
Because of the two functions, it's trying to match two integers. So it finds one integer here, but no integers here. It will have to convert both of its arguments to doubles to use the first function call, but only one of them to a double to use the second function call. All right, and number 27, Ms. Hargrove.
Maybe the double term. No, maybe it's the one.
The first one. Since the first argument is an integer, but there aren't any functions that have a first parameter that's an integer, so it's going to ignore that part and find the best match for the second argument, which is the first function. Okay? All right, let's talk about the homework. We finished chapter 4. That means we'll have another quiz next week. The homework for next week is going to be Project 2. No. Not Project 2.
20.
I thought it was Project 2. Oh, Project, that's a practice program. So we changed it. So we're going to need to have a new project. I don't want you wasting your time on practice programs. All right, well, let's do the project number 4 and output the lyrics to the song 99 Bottles of Beer on the Wall. And I want you to output bottles of beer as words rather than numbers. So let's start with chapter 4, project 4. $99 bottles of beer. And how would we break this down into a reasonable set of steps? We were dividing and conquering. There's something that you can think of that makes sense for a function that we could call? I mean, the main loop itself is just going to be a countdown from 99 to 0, right? Or let's say 100. Um, Obviously, we can write this many different ways. But I do want you to define at least one function besides your main function.
So a countdown function.
However you want to do it. I'm going to have it return bottles minus 1. And if we're going to have the output in this part, I'm going to need what? Using namespace std. All right, so what they tell you to do is use modulus and integer division to extract the tens and ones digits, to construct the English string, and you may need to test specifically for 0, 10 through 19, and so forth.
So just switch statements there.
Sure. Switch statements. First, you're going to have to get the tens part and the ones part.
Is there any step that
And then a switch for each one of those. So it's going to be and you know, if it's less than 20 and so forth. Or if you could say, let's see, if the tens part is 1, you're going to have a special set of
right,
things inside that, right?
for 19 inside?
So how would you start doing that? Any ideas? Anybody have an idea? If we're going to divide it up into tens and ones, we're going to need a place to put the tens and ones, right?
Yeah. So in tens, int, ones,
Okay. And the tens is going to be
1 to 9. Let's start with 9.
But how do we get the actual value of the tens?
But you can originally just assign it to 9 since it's going to start with 99. And then you just
Ah, but we don't know what it is because we're calling it in a function. We just got a value out of the blue. We don't know which value it is because we're calling this function over and over.
Okay.
So,
So it's going to be not. Can it use I?
sorry?
Can it use that integer from main?
No, it can't because that's local to main, right?
Yeah, that's what I was.
We're passing the value of I in bottles. We can use bottles. What are we going to use bottles? So the clue is we're using modulus and division. What does that mean? Mr. Branley, any idea? Ms. Hernandez? Mr. Rahim? Ms. Hargrove?
Not a clue.
All right, well, what happens when we divide one integer by another? Sorry? No. We get integer division. So if we divide bottles by 10, what is that going to give us?
9.
If it's 99 and we divide by 10, we'll get
9.
9. If it's 67 and we divide by 10,
So that's why we're using the homology.
all right,
Because it'll be a remainder.
what do we need to get the remainder?
Bottles divided, a modulus divided by 10.
Bottles, modulus, 10. That will give us the ones part. And now that we've got tens and ones,
Because the modulus is just going to output the remainder.
So if we started with 87, our 10s will now be 8, and our 1s will now be 7. Does that make sense?
Yeah.
So if the 10s is 8, I want that part to say 80. And if the 1s is 7, I want that part to say 7. And I'm going to put those together and say 87 bottles of beer on the wall. 87 bottles of beer. Take one down and pass it around.
So now we can go to the switch functions.
Now we can go to the switch function. And what is your switch going to be based on?
Switch 10s equals 9.
Now, switch 10s is correct.
Case 9.
Case 9. Okay.
Yeah. And then break. And then continue on doing that. And then do a switch function for 1.
Okay. So is everybody getting the idea now?
Would you put your argument for the switch to be like what we were talking about? We need an argument if the statement for bottles being over 1 and 2 or 1 and 0.
So where would you put that? If it's between 10 and 19, then the tens part will be 1, right?
Mm-hmm.
So case 1 is going to have to do something special. And the other thing is that we don't just say 99 once, do we? We say 99 bottles of beer on the wall, 99 bottles of beer. So if we're just outputting it as we get to it, that could cause a problem.
So
We'll have to go through our switch statement all over again.
So we could do, instead of that, you could do a return.
We're going to return something. What I would suggest is something like this. Which means we'll need the string library. Oh, here's a problem. I've got bottles twice, haven't I? And then I can concatenate 9 onto it. Okay? Any other questions? So we've got you started. I haven't handed you everything. You probably run into some nasty problems along the way. If you do, send me an email, include your source code, and I will try and help you out. And I will write this up so that we have the correct problem on the assignment page and everything. We've got about 15 minutes left. If you would like to use that time to work on this problem, you're free to do so. If you need to go clear your head or sleep it off, you're welcome to do that as well. In either case, don't forget the quiz next week, and I will see you then.
Last week quiz get graded yet?
Quiz 2 has been graded, yes.